So here's what we're talking about. We're going to jump heavily into capacitors today. Let me review some of the basics that I talked about last time. A capacitor is basically is an energy storage device. Initially, you just have two neutral conducting plates. But if you connect the capacitor to a battery, the battery basically serves as a pump to get charge off of one plate and put it on the other. So what happens is, since we pretend positive charge carriers are where the action is, even though that's not really true, positive charge carriers get pulled off of this plate, put onto this one, and before long we have equal and opposite charge on these plates. Now, where does it end? Where does the charging stop? Well, it's when the positive plate has become the same voltage as the positive terminal, and the negative plate has become the same voltage as the terminal it's connected to. Then there ceases to be any energetic motivation for charges to further crowd on these plates. Okay? So basically, there's now two equipotential regions in the circuit, this one and this one, and that's when the process is over. And what that basically means is that the battery has taken the two formerly neutral plates, which had no voltage difference, of course, at all, and charged it until the voltage across the capacitor becomes the same as the battery voltage. And that takes putting charge on these plates to make their voltage difference grow. The amount of charge we can get on each plate, first of all, it is, of course, proportional to the charging voltage. So, for instance, if you attach a given capacitor to a 1,000-volt battery, that's going to put more charge on the plates until the voltage difference is 1,000 volts than if you just connected a given capacitor to a 2-volt battery. You don't need that much charge to go on the plates before the voltage difference is 2 volts. So the amount of charge is proportional to the voltage. If you, for instance, if you double the voltage, the charging voltage, you'll double the amount of charge on each plate. But that doesn't mean that every capacitor that you might grab out of a box will have the same exact charge put on it by the same battery. There is also a proportionality constant called the capacitance. So that, let me flip this relation around. The capacitance is a rating for the particular device which tells you how much charge will this store per volt of effort. Okay? So the way I like to think of it is it's the amount of charge stored, and then of course the denominator is the charging voltage, so that's the amount of effort. Okay? So that's our way to rate these devices, and again I want to convey that there's no such thing as being we don't want to rate it as total amount of charge stored, because there's no maximum limit to the amount of charge stored. It depends on how hard you try. If you filled something completely, quote unquote, with a 2-volt battery, if you attached a 1,000-volt battery, it would put more charge. So there's no magic amount for how much is stored. It's just how much can you store per effort. So to give you an analogy, let's say instead of rating this perhaps weird, unfamiliar electrical device, let's say we rate another storage device, a closet, okay? So you and your friend are having an argument about who has the better closet, okay? That's a storage device that stores clothes instead of energy, okay? And instead of energy and charge, it stores clothes, okay? So you make a bet. Your bet is going to be, okay, my closet is better, it can store more clothes, okay? And you think you have it in the bag because you have this nice giant walk-in closet, and your friend, you know that this friend has this tiny little closet, okay? So you know when you both go home and you're going to report back how many clothes you stored, you know you're going to come out on top, right? You've got a nice big walk-in closet, just casually putting stuff in there, knowing there's no way that your friend could get this much in their closet. My closet's going to be better. Little do you know that your friend has rented a trash compactor, and they've taken all their clothes and compressed it into a brick like this, okay, and put a bunch of those bricks into their closet, and they come back and they say, I actually stored more clothes than you, to which you would rightly cry foul because that seems not fair, right? you guys should both agree on the amount of effort you're willing to put into it. And part of that effort is no trash compactors allowed, okay? So this really is the best way to rate any kind of storage, is to not just talk about the amount stored, but put some kind of limit on the effort that you're willing to put into that, okay? So hopefully that makes a perfectly sensible description of why you'd want to rate a storage device this way. There's no limit to the amount of charge you can store, but if you divide by the effort, then there is, right? So for a given storage device, if you connect a 9-volt battery or a 1,000-volt battery, whatever, there's always going to be a certain amount of charge that you can store per every volt that of effort that you're going to put in. Which means that the units of capacitance, in our case, what do we measure charge in? Coulombs. So we have to be careful here because there's actually two different usages of the letter C here in very close proximity. C as a variable means coulombs, that's the unit of charge. But C as a variable, right, not a unit, but a variable means capacitance. What do we measure voltage in? Volts, okay? So the units of capacitance are coulombs per volt. How many coulombs can we store per volt of effort? This gets a name. It's called a farad. The units of capacitance are farads. A 1 farad capacitor is actually a very, very good capacitor. It can store 1 coulomb of charge, which we said was a lot, right? 1 coulomb is a lot of charge. But it can do it for 1 volt of effort. So that's storing a lot of charge for very little effort. It used to be that I would have to report to you that the 1 farad capacitor is like the size of a football field. Okay? Nowadays the technology has gotten so good, we do have ones that you can hold in your hand. Okay? The way they do that, by the way, is by some really crazy trickery, which I'll get into a little bit. But for normal capacitors, we're talking microfarads, nanofarads, even picofarads, is 10 to the minus 12. A farad is not a normal amount of capacitance, just like 1 coulomb is not a normal amount of charge. Okay. Okay. So that is kind of the fundamental definition of what capacitance is. Capacitance is how much charge you can store per volt of effort. This is kind of the equivalent of Ohm's law, right? So Ohm's law, E equals IR, was a fundamental relationship which describes the kind of what a resistor does in its operation in a circuit, right? So in Ohm's law, the voltage drop across it, of course, gives the motivation for the charge to burrow through the obstruction, and we rate the obstruction R by how much current will actually be able to pass at that motivation level, right? So if you present the voltage drop across it, how much or how little charge will stream through, that's the current, well, that depends on the resistance. For this, the voltage drop across it is not so that the charges can pass through. Instead of current, which is the flow of charge, we just have that the charge accumulates, right? So there's a relationship between the voltage across the capacitor and the amount of charge that you can put on it, and the thing that describes that is the capacitance. Okay? And by the way, I guess I should mention that very shortly we'll have both of these things in a circuit, so we should differentiate between the voltage across the capacitor and the voltage across the resistor. So not quite yet, but very shortly we'll have to make that distinction if we have both of those. So just like with Ohm's law, of course, we learned that the resistance of something is determined by its physical properties. How is it constructed? Right? So just to remind you what that equation was, the resistance of something is determined by these physical properties. So let's look at what are the physical properties of a capacitor that determine its capability to store charge or not. Okay? So this is also dependent on how it's constructed. So here, just like I gave you some formula for the resistance, I'm going to have to give you the formula for capacitance. This is for one specific type of capacitor called a parallel plate capacitor. There are other types. We'll focus pretty much exclusively on this one. So this is kind of, I've already been drawing it. It looks like this. It's literally just two conducting plates. And let me give you the formula for what determines the capacitance. So what are the things in this equation? A is the surface area of the plates. They're identical, so the surface area of each of them is identical, and that's A. Okay. And then D is the separation of the two plates from each other. And then this is a constant. I know I'm using the Greek letter epsilon, which we've been usually using for battery voltage, which is over here. It's not the same thing, it's just a different usage of the same Greek letter. It's just a physical constant. I guess let me start with the physical constant. It's not even a new physical constant, it's a repackaging of an old one. It's 1 over 4 pi times Coulomb's constant. So if you wanted to, you could write it, instead of that epsilon naught, you could just, in the numerator, you could put a 4 pi k in the denominator. Then we wouldn't have to introduce a new constant, but it would be more writing, okay? Similarly with Coulomb's law, right? K Q1 Q2 over R squared, you could write it in terms of this. This is just a different way to talk about the same constant, okay? And usually we just choose whichever one is more compact, okay? And in this case, this is the first formula that I think is more compact with the epsilon naught constant, so we'll use this instead of with K. You can compute for yourself what this is. Of course, if you just take 1 over 4 pi times 9 to the 9th, 9 times 2 to the 9th, you can get this number. It's 8.85 times 10 to the minus 12, no surprise. If we divide by 9 times 10 to the 9, it's going to be quite small. And then the units, of course, are going to be the inverse units of whatever the units are of K, which leads us to this. This constant also has a name. If K was just kind of generically Coulomb's constant, because it's in the front of Coulomb's law, this one gets a name as well. It's called the permissivity of free space. Sometimes you'll hear it called the permittivity, so I guess sometimes the two S's will be replaced with two T's. Okay? Now that sounds like a very tantalizing name. Why would you call it that? We'll learn later on in the course why it's called that, but for right now, don't worry about it. I just want to plant that seed. For right now, just understand that all of our electric formulas are going to have K or epsilon naught in them. That's kind of the deal, right? That's some constant that always goes when there's an electric field or electric phenomenon involved, okay? And again, they're just different ways to package the same constant, okay? Okay, so we got that out of the way, the constant. Now let's look at the variables that could actually be up to you in your construction of the capacitor. One of the things that you immediately notice is that if the area of each plate increases, what happens to the capacitance? Increases. Now in my closet analogy, that makes perfect sense, right? If you want to talk about a closet being better, right, storing more clothes per effort, one of the ways it's better is it's bigger, right? Well, same thing here. If the plates are bigger, larger area, then the charge has more room to spread out, okay? And if it has more room to spread out, the voltage buildup won't be as fast. You're going to have to put more charge on there before it builds up to the battery voltage. Okay? So this is just more room to spread out. We don't put these charges in some tiny little pen, right? We cram them in there. We have lots of room to spread out. And if you have more room to spread out, you have a better storage device. And again, the capacitance being larger means you can store more charge per effort, more charge per volt. So that one is the obvious one. That is, of course, perfectly analogous to my closet example, but the other factor is not. So here we're going to have to leave that your bet with you and your friend about closets behind and just kind of try our best to motivate. One of the other things you see, if you want to make your capacitance better, what should you do to the plate separation? D. You should make it smaller. Now here I'm going to try to sort of hand-wavily prove this, but again, I don't want to dwell on it too much because I don't think it's that instructive. So why is it that putting the plates closer together makes the storage device better? It's kind of hard to motivate, but one thing that I will go back to, you guys learned about the relationship between electric field and voltage, right? And electric field talks about, the stronger the electric field is, it's because the slope or change in the voltage over distance is more precipitous. If the voltage changes rapidly over a short distance, then the electric field will be larger. This formula is useful in its own right, so let's adapt it to our current circumstances. Of course, we haven't called delta V in a long time. For the entire circuits discussion, we've called just the voltage drop from one place to the other V. In this case, we also know what is the distance over which the voltage drops is, of course, the D, the plate separation. So with that in mind, let's examine two scenarios, one in which the capacitor has the plates close together, and one where the plates are further apart. And let's find out why is it that one, I guess I should do them in the opposite order so we can see why it gets better. So why is this worse, and why is this better storage device? Okay, so this has a lower capacitance, and this has a larger capacitance. And again, I'm going to do this somewhat hand-wavy, but I'll do my best to motivate this. Now, if I connect these two capacitors to the same battery, right? It's the same, 9-volt battery, right? The whole deal is that if I connect both of these capacitors to a 9-volt battery, the 9-volt battery will bring the voltage difference between both plates up to 9 volts, and then the charging is done, right? So V in this case is going to be fixed. But according to this formula, if we have a certain voltage difference, say 9 volts, but it's a very rapid change, right, in a short distance, if we lower the plate separation, what does that do to the electric field? It increases, right? So this implies a larger electric field. So if I draw in the electric fields in both of these, let's say as in my drawing over there, the top plate's the positive plate. So this one will look more like this, and this one will look more like this. I purposely try to draw the line density much higher on the right to indicate it's a stronger field. Now here's a common misconception. If you look at, say, a point halfway between the plates, common misconception here is that, oh, okay, that makes total sense that the electric field is stronger here because you're much closer to both plates. Well, remember that when we talk about plates, we basically usually approximate them as infinitely long, and then it doesn't matter how close you are to the plates because the field is uniform anyway. So the field there is not stronger because you're closer to the plates. The field here must be stronger because there's more charge. Okay? So if the field is stronger here, there must be more charge creating it. So it looks like that. So again, if there's a stronger electric field being made by a uniform plane, it indicates more charge making it. So notice this is all inferred. I'm not saying why this is occurring. I'm just saying, well, this must follow from this for whatever reason. So if there is more charge, but remember our whole premise was the same voltage, right? So we store more charge for the same voltage. Well, we've just shown that this must imply more capacitance. So these two things right here, more charge at the same voltage must imply larger capacitance. That's been the best way that I can motivate this for you. I know that there's some gaps in there, and then I just want to kind of leave it at that. Okay. So those are the two things that you can do so far. Anyway, we'll get to a way to soup up our capacitors a little bit later. But those are the two things that you can do to improve your performance of your capacitor. You can make the plates bigger, or you can make them more close together. Those will both make it a better capacitor. Okay. Are there any questions on that? Okay, so there's one more thing we need to do before we move on to starting to actually construct these things, circuits and whatnot. We need to establish not only about charge storage, but energy storage. We mentioned that along with this comes energy storage. Let's figure out what that is. So here we have our plates initially. There's no charge whatsoever. They're both neutral. And as you can probably guess, there's no energy stored there either. Okay, there's no accessible stored energy. And let me draw kind of a sequence of events going to the right here of the charging process. Well, basically what we're doing is we're taking charge off of one plate and putting it on another. We're slowly creating a charge separation. Now obviously the battery is the pump that's doing that, but it doesn't really matter how we're doing that, because at the end of the day, the amount of energy we have stored should be due to the properties of the capacitor, not the particulars of how that got done. So the very first thing we do is we take a positive charge, we take it off of one plate and put it on the other. Now this right here stores basically no energy. That positive charge that arrives at that plate has nobody to repel from, okay? So the energy, added energy here is basically none. If we go over here to the very end, if you've already have a bunch of positive charges that are on there from previous trips, I guess, then this one, that one stores a lot of energy, right? So cramming that last positive charge on there, think about how many other positive charges are already there, and you're trying to shove it right next to them. So here, this charge, so the last charge, has the most potential energy stored, okay? Think of it like the very first charge you put on the top plate there. It's got the whole plate all to itself. And the last one is the hard one, because you're trying to put that positive charge where there's already a bunch of other positive charges that came before, right? And in fact, on this last one, Q, the voltage difference is already built up to the voltage difference of the battery at this point. So at this point, this one stores basically the most. So the last one, remember our good old formula Q times V, right? But let me point out that not every single charge had that situation. The ones on the beginning were easier to put on, and the ones at the end were the hardest to put on. They stored the most energy. So what should we do? If we wanted to use this formula as a whole, and we wanted to use Q, capital Q meaning the total charge, right, everybody, so that's these guys. We cannot use the voltage drop at the end because that is way overcounting the amount of energy we stored. If we just use the voltage at the end, well, that's basically saying that the charges have always been going across the voltage difference the whole time, but they haven't. The voltage builds up with the charge, right? It's these charges which are creating this voltage. So what we have to do, we have to use, if we're going to use the total charge, capital Q, we have to use the average voltage that was experienced. And that voltage built up from nothing to whatever it is at the end, right? It's the charges themselves that built this up. So here's where I tell you, what was the average voltage experience from the beginning to the end? Well, it was halfway, okay? So the average voltage is actually going to be experienced was half the final. And for those of you that may be comfortable with this from math class, how do you know it's exactly halfway? Well, these are linearly proportional. And it means that any linear function, if you take the average, it's halfway between the endpoints. Okay? So the extra factor of 2 makes sure that we don't overcount. Because remember, this voltage difference was not in existence before. It was the charges themselves that caused it. Okay? We go from the early charges, which there's basically no potential energy stored yet, to the end, where the last drops of charge are the hardest to put on. And the average voltage difference was halfway. So here's our formula. We're done. The potential energy formula for how much energy is stored in a capacitor is 1/2 times the charge, the eventual charge, and voltage. Okay? So if we compare that, of course, we have 3 forms of the power law. We put them in the order that I originally put them in, not that it matters. So we had 3 different forms of the power law for resistors. And of course, that's not energy, it's power. That's the amount of energy per time, right? It turned out to be a more sensible question for a resistor, right? Because the resistor, there are always charges coursing through it. So a better question would be, what is the rate at which energy gets transferred per time from electrical to heat, right? And we said, of course, that we had, this was more useful for series because the current is always the same in series, and this one was we used because this was always in parallel, and voltage is the same in parallel. So it's not that the other ones are wrong, but it's hard to make a mistake. Well, we're going to do the same thing with capacitors. Here's our first form. And notice now it's not a rate, it's just the amount. the amount of potential energy that's stored on a capacitor. So it's just straight up energy, potential energy. And where are we going to get the other two forms? The same exact way we did before, right? We got these other two forms of the power law by subbing in Ohm's law, and now we're going to do the same by subbing in the equivalent of Ohm's law for a capacitor. So for instance, we could put in Q equals V times C, right? And get rid of Q, or we could solve for V and put in for, and get rid of the V. So let me give you what those are. You could have 1/2 Q squared over C, or you could have 1/2 CV squared. So there's 3 different alternative forms. Why do you want to have 3 different forms of it around? Well, same reason. When we get to series and parallel, which I'm not going to do right now, we're going to find that some forms are easier to mess up and some are harder to mess up. Use the ones that are harder to mess up. Which one do you use for series? This one. How do I know? And this is again spoiling a little bit of the punchline of series and parallel caps, which we won't get to quite yet. Instead of I being the same, right, the flow of charge, it's going to be just charge. So instead of I, it's Q. Okay? So that's why we use that one. And then over here, we know that voltage is the same in parallel. Same thing here, voltage is the same in parallel. So I guess I can put the corresponding quantities, I can circle them. Flow of charge is the same in series. Charge is the same in series. Voltage is the same in parallel. Voltage is the same in parallel. Okay? Okay, any questions on that? Yeah?
Can you draw a graph to show what's the potential energy for parallel and series?
As I mentioned, I'm going to push off series and parallel because I want to talk about stuff that the homework is harder problems on the homework first. Okay, so I'm going to come back to series and parallel in a big way, but later on. Right now, I just wanted to have 3 different forms of the potential energy formula available. So let me come back to that later.